All right. Hello, everyone. Welcome to episode 15 of Warsaw AI. I'm very happy that you are here with us. It's the first stationary event after more than 2 years, in fact. Hopefully, we'll stay with on-site events. And today, this meetup will be dedicated to explainable machine learning. We'll have 3 fantastic speakers. So first, Paweł Olszewski from Allegro will give a talk, Use Your Data Wisely, Data-Centric NLP in the e-commerce domain. Later, Mateusz Krzyziński will tell us about extensions of the SHAP method. And finally, Tomasz Michalak will tell us about improved feature importance computations for 3 models. And at the end, we'll have the after party for at least 1 hour. So we hope that you will enjoy this event. Feel free to ask questions at the end. So each talk will last about 20 minutes. And after each talk, there will be Q&A session for about 5 minutes. All right, enjoy. And I think we can start and invite our first speaker. Paweł, the floor is yours.
Okay, so hello, my name is Paweł Olszewski. I'm a research engineer at Allegro. And today I will be talking about a project that I have been working on and how we use the data available on the platform to build the machine learning solution for this project. So what is this project about? As you may know, at Allegro we have offers, and each offers consists of 2 main sections. The first section is the parameter section, where the merchants fill the parameter name and parameter value. The second part of the offers is an offer description, where the merchants deliver the description of the product. And our goal of this project is to enrich the parameters value based on the offer description. So we can, in the offer description, we can find the parameter value. Here is the parameter brand. And then we can fill out this value to the parameter section. Similarly, we can find the parameter model and enrich this value in the parameters section. Okay, so this is our business goal. And now, as you know, to build the machine learning solution for this problem, we have to gather the data. And now I will describe you how we approach in the first iteration, how to build the data set for this problem. And as you may expect, this process, one more thing, because we have to define on which level we want to enrich those parameters, because at Allegro, we have 15 departments, we have a lot of categories in those departments, and we have a lot of categories. This category tree is quite deep, and we have to decide whether we want to enrich the parameters value on the category leaf level or on some higher category. And in this presentation, we will focus to enrich the parameters in the single department, and it will be department electronics, and we will enrich the parameter brand. Okay, so as you may expect, the data gathering process is really slow and expensive. Based on the literature, we estimated that to build such a model, to enrich a single parameter in a single department, we have to collect at least 7,000 examples to training and some examples to validation. And we hired 3 people. This annotation process took 1 month for these 3 people, and it was full-time job for them. So yeah, it's quite expensive. It was slow, but we collected the data. And now you can see why this process is so slow and why it's expensive. Here you can see the screenshot from the first iteration of this task, where we ask our annotators to mark occurrence of each parameters defined at the very top in the offer description. So here you can see some errors that was made by our annotators. Yeah, and it's long, expensive process, but also there is a background process. But let's define the model now. In the literature, this problem is called the named entity recognition. And to solve this problem, we use the BERT-based model architecture. And it was as follows. For a given sentence, we use some language model earlier pre-trained. I will describe this model in a couple of minutes. And this model for each token computes the hidden state. Then we used additional classification layer. And this classification layer was classifying whether a given token belongs to an entity or not. So in this simple example, we can see that here we can recognize that the first entity, that's company. And the second entity, it's also the company. Let's say that Coca-Cola is a company. And here the B states from the beginning of an entity. I, it's from the inside of entity. And these things are a design strategy how to how to build the classifier. And this design strategy help us to recognize whether the tokens belongs to the same or different entities. It's only the design strategy, and there are a couple of methods to do that. Okay, and the rest of tokens are marked as out of entity. Okay, so we have defined the model, and now I quickly introduce the metrics that we use to evaluate this model, because in the literature you may find that such models are evaluated this way, that it's important whether the model were able to find all occurrences of the parameters that exist in the description or in some text. But from our business point of view, we are interested only to judge whether the model was able to find a single description, the single parameter value, and whether it was correct or not. So then we can compute the basic metrics like precision, recall, and F1 score. Okay, so we trained this model using the backbone, as I said before. We use the Polish BERT. In the literature, you can find this model called Herbert. It was trained by my colleagues from Allegro. And let's see the results. For the department electronics and for recognizing the parameter brand, the F1 score was about 92%. Okay, so these results, it's quite nice as a first shot, but how we can improve our model now? First of all, let's think on which data the Polish BERT or Herbert was pre-trained. So the data was Wikipedia, Wolne Lektury, Open Subtitles, Oscar, and some Allegro data, but it was just a promille of the whole corpus. And now, if we think, we can visualize where is the Polish domain of language. It's something here, but we indeed are in e-commerce domain, so we can visualize this domain something here. And then when we will think about our downstream task, it's probably something here. Okay, so based on the paper published by Allen Institute, we decided to pre-train our model on the e-commerce data to improve the performance on a downstream task. We call this model Herbert, and this model based on the Roberta architecture. We used 120 million offers to train this model. We used 8 GPUs, NVIDIA A100, It took 24 hours and it was pre-trained only one epoch. The vocabulary size was 50,000 of tokens. And we add here one modification that I will describe in next slide, the whole word masking tokenizer. Okay, so what is this whole word masking tokenizer? In the original BERT paper, the masking strategy of tokens, it's that we are randomly masking some of tokens and we don't care whether the tokens belongs to the same word or not. And in this tokenizer, we are masking only the whole words instead of single tokens. And when you think about our task, it makes sense because we are interested in predicting whether the whole word belongs to an entity or not. Okay, so now let's see the results. The model trained with Polish BERT was about 92% of F1 score, and the model with NERBERT achieves 97.3% of F1 score. So it's really nice results, but we trained only single model for single department and for single parameter. But let's think how long the annotation may take if we would like to enrich more parameters across the whole departments. So we have 265 million active offers every day. We have 15 departments, thousands of parameters and let's make a simple estimation how long the annotation process will take if we would like to enrich only the 50 parameters in each department. So only the most important one. And let's assume that we have this team that consists of 3 people and the annotation process will take about 62 years. Okay, let's assume that we will be able to hire 100 people. The annotation will take 2 years. Okay, basically in this point, we can say that we are not able to satisfy the business condition and we can start a new project because it's no makes sense to continue this process. But maybe there is some way to improve the data gathering process. And the answer is yes. And how we can do that? We can once again use the data available on our platform, but this time other way around. So now we have a lot of offers that have already filled the parameters like brand or model. And here we can take such offers and then try to find the occurrence of this value in the offer description. So here is for parameter brand and for parameter model, we can make the same search and we are looking only for exact matches. And this way we can build the training data set for our model and we called this process pre-annotation. Okay, so we collected the data set that consists of 7,000 examples and we trained our model using NERBERT backbone and we evaluated this model on the same data set collected by humans. And the results are the following. The model trained on the automatically annotated data achieved about 93% of F1 score. It's quite good result, but we were thinking, what is the reason? And let's think about when the data were collected. So the data collected by humans were collected like 9 months ago. And the data to train this model on automatically annotated data was collected 2 weeks ago. So here we can observe the data drift problem. So how to make the fair evaluation of our model? And now we can once again use the data from our platform and use once again the data that have already filled out this parameter by our merchant and make predictions using our model and compare the results. So here you can see the table where is a description. We have a target that was filled by the seller and predicted value by our model. Now we are able to compute the metrics without any human annotation. And we compare this. We use this approach. And now we can see that model trained on automatically annotated data achieved F1 score about 96%. So it's more or less on the same level that model trained on data annotated by humans. Here you can see that model trained on data annotated by humans achieves on this data set 90%, but here again we can observe the data drift. So it's not fair evaluation this time for the model trained on the data annotated by humans. Okay, it's a perfect solution. From one hand, we can have almost unlimited annotation in a really short time because as I show you, we have a lot of data. But on the other hand, this approach doesn't work for all parameters. For example, let's think that we have the memory, like memory RAM, and there is a value 4. So this method will not know whether this particular value 4 is for the parameter value or for something different value. Second pros of our model is that the annotation are robust. What I mean here, as I show you at the very beginning, the annotators made a lot of mistakes in this short example. But here, when we are looking for exact matches, we know that the annotated parts will be exactly what we want to have. But it's just remark that we have to believe our merchants that the filled parameters are correct. It's rather a minor problem, but there are some cases that the parameters are wrong. And the third pros, maybe the most important for us, that this process gives us an ability to compare, to verify different hypotheses. So for example, we can dump the data from different distributions and see which model will perform the best on the production data. So it's really, really nice property of this method. And now I would like to show you some other results. We trained our model for different departments and for different parameters. And all the results were about 90% or above. Even for parameters like model, where the parameters value are rather unique. So when we are training the model for recognizing parameter brand, the brand it's in many offers, but the model it's rather uncommon entity. Okay, and what are our next steps to develop this project? First of all, we can use once again the data on the platform and condition our model by category to improve the results and recognizing parameters value in given categories. We have to think how to improve the data annotation process. I mean the quality of the data, because as I said before, there are some cases that the annotations or the filled out parameters are wrong. And we have to build a solution that will be able to process longer description, because currently we are truncating our descriptions in 512 tokens. And it's all from my side. Thank you very much for your attention.
Okay, thank you, Paweł. Thank you very much. It's time for questions. Do we have any questions? Okay, so give one microphone.
Thank you for your presentation, and I just wonder, did you prevent from any leak between train and test set? Because the test set was gathered by merchants like online, and did you filter out any like the values which could, or the description which were the same as in the train set?
Of course, yes. So the offers were filtered out, so we didn't have the same offers in the training and the test set. And we made also some tests how our model can generalize. So I don't have here the results, but we trained a model on all departments without home and garden departments in a training data set. And then we conduct the evaluation in the home and garden data set department for parameter brand, and the results were about 87%. And then we make one more iteration where we remove from the test set all values that occurs in the training data set. And then the results were about 77%.
Okay. Does it answer your question? Okay, great. Do we have any more questions?
Thanks for a great talk. If I got you correctly, the best model you've had, so the one for a brand in electronics, it had those metrics around 97%, 96, 97. So even though it's really high, it still does make some rare errors. And I've been wondering if you were to put this model into production, it would still occasionally make errors. So does this model come with some certainty measure so that you know which of those could be wrong, or are you okay with having some of those offers labeled incorrectly?
Okay, it's a really great question. So at this time, we are taking the prediction with the highest score, but we are going to develop some uncertainty measure because it's rather uncommon research to measure uncertainty for an identity recognition problem. So we are currently working on that.
Okay, great. Do we have more questions? Still have about 2 minutes. So maybe I will ask one. You said about this human annotation and automatic annotation. Have you maybe thought of or tried combining these approaches? So for example, improving the automatic annotation using human annotation. And do you think that it may help in your case?
Yeah, we thought about this, and it depends on the parameters indeed, because as I show you that of some parameters, this process will not work, but we can make such pre-annotation and ask our annotators to check whether the annotation made by this process are correct or not. So this way we can somehow speed up this annotation process.
Okay, great, fantastic. All right, I don't see more questions now. So I think we can thank Paweł once again for a great presentation. Thank you, Paweł.
Thank you very much.
And now we can invite our second speaker, Mateusz.
Hello, everybody. So the Warsaw.ai website says that Warsaw.ai is a vibrant community of AI practitioners from technology companies, startups, and academic institutions. Therefore, before my presentation, I wondered how much I should dive into details. However, from my experiences with business and what I have read, for example, on Polish ML community Discord, the topic of explainable AI, XAI in short, is not yet commonplace. Even Gartner's hype cycle for AI indicates that topics such as responsible AI and human-centered AI are still in the innovation trigger phase. And thus, I decided today that my presentation will not be too detailed. So I will tell you about the methods of explainable AI, which are some extensions of the SHAP method, and maybe try to convince you to be more interested in this topic, in this area. But first, a few words about me. So my name is Mateusz Krzyziński, and I'm data science student at Warsaw University of Technology. And currently I'm taking my first steps in world of science, working as a researcher at MI2 Data Lab, led by Przemek Biecek. So let's start with a small introduction, or maybe reminder for some of you of the original SHAP method. And firstly, SHAP stands for Shapley additive explanations, and it is a method based on the concept of Shapley value, which is the concept from cooperative game theory. And SHAP is additive feature attribution method. What does it mean exactly? So consider this simple example on slide of this simple model, black box model, predicts rental prices for Warsaw based on the 3 variables mentioned here, area, floor, and whether this apartment is pet friendly or not. And SHAP can be used to explain how each feature of a given observation influence the prediction of the model. For example, the slide shows that possibility of having cat increase the rent for an apartment by 400 zlotys compared to the average. But attributions of all variables summed up to this background value of 2,200 zloty of is prediction for selected observation. So the question arises how to calculate Shapley values, and well, calculating the attribution of variable I is based on analyzing how adding this variable to the subset subset S of variables will affect the value of the function ES here, which may be seen as prediction of the model when variable in this set S are specified, and the contribution of variable I is calculated as a weighted average over all possible subsets. So obviously this is computationally expensive, and that's why Shapley values are often estimated in other ways. But I believe that the next speaker will tell a little more about it, and I personally can't wait for it. But for now, for sake of completeness, let's see how the explanations obtained using this method look in practice. And on the left, we see an example from the SHAP library package, SHAP Python package, related to the paper that introduced this method, actually. And on the right, we can see an example of local explanation from a Dalek Python package, and it is package created by our lab, MI2 Data Lab. It was example, and now let's consider why actually I'm talking about this method and not about any other. And this is because the immense popularity of this method, and it can be seen from the number, for example, from the number of stars on GitHub for repositories related to XAI. And SHAP is by far the leader with more over 16,000 stars right now. And as you can see, the next one, the Lime library, still did not break the 10,000 barrier. But the question is where does this popularity came from? And of course, a lot is a matter of promotion, recommendations, maybe also luck. But what is worth mentioning from our more theoretical point of view is that SHAP has some expected mathematical properties, such as local accuracy, missingness, and consistency. And these properties leads also to properties of symmetry, null player, and additivity. But it is more, it will be more in the next talk, I believe. So let's further. And yeah, this is why SHAP method and Shapley values concept are used as a source of inspiration for developing another XAI tools and other techniques. And let's see how SHAP can be extended to other subdomains. And let's start with a specific application in survival analysis. But to get to that, we need some kind of brief introduction to what survival analysis actually is, because maybe it's not so popular. And to put it simply, it is often modeling on right censored data. And censoring is best described through an example. For example, we have a study conducted to determine the mortality rate of a group of patients after diagnosis, some kind of particular disease. And if a patient dies during this study, their outcome is death, and their time of death is known. So it is depicted here in these red dots. However, if a patient drops out of the study before they die, then their time of death is not known. So we don't know what happened next. And survival analysis is kind of tools that can help use this kind of data. Okay, and moreover, in survival analysis, instead of just predicting one single time moment for an event, actually we predict specific function called survival function, and it describes probability of an individual surviving until time t without experiencing an event. But let's maybe move to more machine learning perspective. Okay, and relative to other areas of supervised learning, development in survival analysis has been slow, but when looking at the number of search results in Google Scholar, we can see that the number of papers in this area is increasing year by year. And we need to know that survival analysis actually has essential applications in healthcare, finance, engineering, and more areas. And from my point of view, the most important was the use in medicine, because I work with a team of medics conducting research on uveal melanoma. It is kind of eye cancer. And I wanted to convince them to use more advanced methods than just simple statistical analysis. And however, for this purpose, I needed appropriate validation of such kind of models and also methods for explaining the value predicted by more complex ML models. It turned out that there are actually two significantly different methods. One is Survlime and the counterfactual explanations for survival analysis. And there are several versions of Survlime, let's say, that only slightly differ between each other, while the idea behind is kind of similar. And the idea is to find a Cox proportional hazards model to approximate this black box survival model, and this Cox proportional hazard model is actually the most known model in this area of survival analysis. However, the biggest disadvantage of these methods presented by gentlemen listed below is that there is no open source implementation. So we see that some methods already exist in survival analysis, but what else can be done in this area? And well, my idea is that SurfShap can be done. And what is SurfShap? And as I mentioned before, the primary motivation was the need to explain black box model used in medical applications. And the main idea is that SurfShap is the generalization of the SHAP method for this specific case. And the assumption was to use concepts which are directly related to this area of survival analysis. And that's why the explanations are based on this survival function that I mentioned before. And another important assumption was to create an entire framework, actually, of of explanation methods. And in addition, it is important that the package under development will be very soon available as open source solution, and it is compatible with other tools created by our lab. So let's look at the base example. That is a single local explanation for a selected patient. And all the examples that I will show will be related to the model based on data that I have been working with recently, which is the data containing information about these patients with uveal melanoma, this cancer. So how does SHAP work? It can be thought that in this method, the impact of given variable is calculated at different times from the moment of diagnosis. And the size of an impact can vary over time, and even the nature of this impact may differ. For example, here we see that one of these variables in certain time increases the risk and then decreases the risk. Maybe, okay, and yeah, this vertical line is the information about the real outcome for this analyzed patient. Okay, and where does this Shapley come from actually here? So naturally, the method operates on discretized time. So the values are calculated at each of these time points simultaneously. We use the Shapley sampling method as well as the estimation based on kernel SHAP equivalent for this case. And this kernel SHAP equivalent is based on functional regression in so-called scalar covariate functional response scenario. And of course, for more sparse results, the lasso method for functional data can be also used. And another concept from functional data analysis included in this solution called functional depth is used to sort variables by their importance. And at the global level, we can first of all check the simple importance of the variables over time. And here we can see that the importance of the variables for the model prediction does indeed change over time. And we can also create an explanation similar to the SHAP summary plot and look at the distribution of attributions for individual observations depending on variable value. And here we can compare, for example, the effect of age for prediction over time for all patients. And we can see that it is not straightforward as lines intersect. But for the sake of simplicity, we can also look at this distribution in different way, listing just the observations that are outliers. And for this purpose, we use the functional box plot. And the functions indicated as outliers are marked with colors representing their values. And the purple line is functional median, and these orange lines are actually the upper and lower whiskers of functional box plot. And another way to look at the impact of given variable is to see average impacts across group of values. So thanks to this grouping of observations, we can use another concept from functional data analysis, which is ANOVA for functional data. And I believe that it is quite important possibility in this area because the survival analysis has strong statistical foundations. And in addition to such kind of maybe more informative theoretical explanations, we also need some statistical tests that can be applied to black models to validate their predictions. So yeah, it was a quick presentation about some possibilities of this package that I'm currently working on and will be soon available as a Python package and also in the R package library. But now I would like to move on completely different, move on to something completely different, but also very interesting. And it is an issue concerning methods based on Shapley values also. And I would like to present Shapley flow method, which was proposed by Lundberg, which is one of the author of this original SHAP paper. And so far, I have spoken about SHAP in superlatives, but it has its drawback, of course. And the usual SHAP and also many other methods may be problematic in case of correlations in data. And it means that when features are dependent on each other, perturbations that are made to calculate Shapley values will cause extrapolation to areas out of data manifold. So one way to deal with this problem is to use causal graphs, and they describe dependencies between features. But several explaining methods that use this kind of graph have been developed, and they also have their drawbacks. So Shapley flow is proposed as an attempt to just rectify this problem, this situation. Let's look at a toy example. We have a slippery prediction model that takes an input for features, the season of the year, whether or not it's raining, whether the sprinkler is on, and whether the pavement is wet. And although a model takes 4 variables as an input, we arbitrarily assumed that it only depends on x3 and x4 directly, and existing approaches that ignore this causal structure assign 0 importance to the season, x1 variable, since it only indirectly affects the outcome through the other input variables. And this is actually the result from casual SHAP, independent SHAP explanation. Okay. And the next one is asymmetric Shapley values method that leverage the causal structure among the input variables when assigning contributions. And it solves the earlier problem of ignoring indirect effects, but it does so by ignoring direct effects of variables x3 and x4. So the question is how to do it better. And the answer is Shapley flow explanation. And as in ASV mentioned before, the relationship is described by causal graph. However, unlike in ASV, attribution is assigned not to the nodes of this graph, but the edges, which are relationships between variables. And an edge in this graph is important if its removal from graph would change the predictions of the model. So the question is, what is exactly the edge removal? And in the context of feature attribution, in which we actually aim to measure the difference between output of a model for selected observation and for some background prediction, this means that target node of the edge still relies on the source background value as opposed to the source foreground value, which is a value for selected observation. And the edge attribution has the additional property that for some explanation boundaries, calculated values are the classical Shapley value. For example, here F2 boundary corresponds to the ASV mentioned before. And such an explanation result actually eliminates the need for multiple explanations in bar plots. And at the same time, it gives a broad, holistic picture of the situation. However, the big disadvantage is that use of this method requires the knowledge of the dependency structure in the form of directed causal graph, which becomes quite complicated with the increase of the number of variables. And the explanations visualized throughout this graph are similarly complex, as we can see. However, the research questions formulated in the paper, which introduced this method, Shapley flow method, are also connected to this problem. For example, can Shapley flow work with partially defined causal graphs, and how to explore this attribution when this graph is complex. And I believe that these questions are very interesting in terms of research in this area, XAI area. To sum up, today I have shown the intuitions maybe behind the most popular method of explainable AI currently and its exemplary extensions for specific cases. And for more information about XAI and about our projects related to human-centered AI and responsible machine learning and explainable machine learning, please visit our webpage, which is mi2.ai, and also our blog about responsible ML. So thank you for your attention, and thank you for this opportunity to show something today.
Thank you, Mateusz, also for accepting our invitation and very nice talk. Do we have any questions to Mateusz? So the next talk will be also about Shapley value, but also about the Banzhaf value. But first, let's ask some questions to Mateusz. I have one question. Can you maybe tell us something about efficiency of these methods, of the methods for calculating Shapley values for different problems in terms of time complexity, for example, or how much time did it take to run experiments that you described?
Okay, there are no slides about it, but in terms of my method that I'm currently working on, currently we use to estimate Shapley values, Shapley sampling method, which is computationally expensive and also not so good because of, I don't know maybe how to say it, but the results are not so reproducible. But we use also kernel SHAP, and with use of concept of functional regression in this scenario, it is maybe more stable results here. But yeah, I believe that the next speaker will talk about properties of Shapley values and mathematic I don't know, features of this method.
Yeah. Okay. Good. All right. We have time for maybe one more question. Oh, there are two questions actually.
Thank you, and thank you for a nice talk. My question is actually very, very basic. Could you move to the next slide, please? Yes. Or maybe even the next one, please. Okay. Yeah. So I don't work and I have zero experience with this medical domain. And looking at this diagram, I have no idea what's going on in here. I don't know what's on the x-axis.
Okay. So
and I don't really know how to interpret the y-axis. I don't know if SHAP value of minus 0.4 is good or bad. Is it big or small? I just have no idea what's going on in here. So if you could please explain it a little bit more, I would be very grateful. Thank you.
So actually every line here is for one patient in data set, and the color depicts the value of variable age at diagnosis, and y-axis is SHAP value. So this is attribution of this variable for prediction for this patient, for this individual patient. And the prediction is in form of survival function. So it is a function between 0 and 1. So the positive values here are positive in terms that it is good that the probability of survival to time t is higher actually if the SHAP value is higher, if the value of survival function is higher. So positive SHAP values are better, and the x-axis here is timeline, is time here measured in weeks. So yeah, it's just time, and these numbers under are informations about data. So each event is actually recorded depth in this data set, and censored is that we have no information about this patient. For example, if there are 7 under 400 at timeline, it means that 7 people, 7 patients live up to 400 days, but we don't know if they die at 400 and first day, or maybe after even more weeks. So it is kind of explain of this plot, summary plot. I don't know if.
Okay. Looks that it answered the question. Great, thank you, Mateusz. There was one more question, I believe. Okay, so it's already answered. Okay. Do we have more questions? If not, I think it's time for our first speaker. So first of all, let's thank Mateusz once again. Thank you. Okay. So now Tomek Michalak will also tell us about Shapley value, but also about Banzhaf value, right? It will be improved feature importance, computations for 3 models. So Tomek, we can start.
Thank you very much. Thank you for having me. So let me start with a tribute to the main authors of the paper. I was only invited to the team later on as a game theorist, so my talk will be more game theory oriented. So let's start. Thank you. We have recently published this work at the conference on uncertainty in AI. It's going to take place in Eindhoven this year, and it's still work in progress, and I believe it's very interesting, and it actually relates a lot to these extensions that Mateusz has just described. So, well, I don't have to talk about this SHAP thing that you just heard about, and there is a strange thing I didn't coordinate with Mateusz. I mean, it was complete coincidence, so thank you to organizers for choosing the topics very well. So there is this algorithm for computing the Shapley value explanations for 3 models published a few years ago by Lundberg and colleagues, and it works in polynomial time. So what we are going to well, my talk is going to advocate to you that you can use the Banzhaf value for 3 models. And well, there are a few reasons for that. First, it's noticeably faster, and I'm going to show it to you. We believe it's more numerically stable. And in our experiments, it comes out that it essentially delivers you essentially the same results. And on a meta level, my talk is going to give you a perspective of a game theorist. What I'm going to show you is that there are a plethora of different game theory solutions, not only the Shapley value. And what I mean to say is that all these other methods are neither better nor worse than the Shapley value. They are just different, but they may be better suited to particular applications you have, right? So for instance, those graphs that you've just seen, there are special methods in game theory to deal with values on graphs, and maybe that should be used, not just an extension of the Shapley value. And there are also very interesting computational results in computational game theory that you can directly apply in your computations, and you can probably come up with some faster algorithms. So that's the plan of my talk. I'm going first discuss values in cooperative game theory. Then I'm going to talk about algorithm, and finally I'm going to show you the results of the experiments. So let's start with values. Okay, so what's a collisional game? A few slides that are going to explain the previous slides that you've just seen half an hour ago. So you have a collisional game is defined by the set of players and by the characteristic function that assigns values to each collision. And the only assumption about this, the characteristic function is that the value of the empty set is 0. And there is this ongoing debate how to correctly define this value. I mean, this value function, the characteristic function in the context of explainability. We are not going to get into that topic today because we don't have the entire night for that. It's a very, very, as I said, there is a very heated debate in the literature now how to define this function in the context of explainability. Anyway, let us consider this function. These values, this characteristic function. You can see you have symmetric players, and there is very nice, interesting property that there is profit from cooperation. So in early days of game theory, there was this assumption, that the grand collision, so the collision of all the players, is going to form. So here you can see that the players earn 24, and the question is how they should divide the payoff from cooperation. And that was a very, very important question that, you can answer in very many ways. There is infinity of divisions you can come up with, and you can be interested in stability of division, but you can be also interested in fairness, and we focus on fairness. So if you want to talk about fairness, then first you have to define it, and typically you use an axiomatic approach. So let's talk about an axiomatic approach, about axioms. And when you talk about axioms, let's talk first about assumptions about axioms, so axioms about axioms. So what do we want about, how do we want to distribute these values? So our first assumption is that we want to enumerate the agents according to how they contribute to the game. Then the question is how to measure this contribution. And the answer comes from economics, from the concept of marginal contributions, which is basically how an agent contributes to the collision, the value of the collision with an agent minus the value of the collision without this agent. And also the last main assumption we make is that we want to look at all possible marginal contributions in the game of a player in the game. Okay, so the first axiom is symmetry. So if you have two players that always contribute the same to every collision, they should get the same payoff. The next axiom is null player. If you have a player that does not contribute to any collision whatsoever, then this player should get the 0 payoff. Finally, furthermore, you have additivity. This axiom basically says that if you have additive games, the payoff should be also additive. And let me show you the example. Here you have two games, game 1 and game 2, and then assume that you have a game 3 that is a sum of these two games. Then the payoff of game 3 should be the sum of payoffs of these individual games. So that's additivity axiom. And interestingly, there is a very natural formula that satisfies these three axioms. And this is this formula. It's basically average marginal contribution of a player to all the coalitions. Right? You see, that's the sum over all coalitions to which the player does not belong. And then we have the coalition with this player minus the value of the coalition, and then the average, right? And you can see symmetry is satisfied, null player is satisfied, additivity is also satisfied. Example, player 1 contributes 5 to the empty set, 1 to player A2, 1 to player A3, and 1 when the ground collision, when player 1 joins the ground collision. So in total, it's 8. We divide by 4, the number of all marginal contributions for this player. So the result is 2. Now we may compute it for the 3 players, and this is the payoff vector that we found. And when you recall, well, one of the problems you can see is that, well, one of the problems you cannot see, but well, it's there, is that it's not unique, meaning that these 3 axioms do not uniquely determine this value. I mean, this division method. The second problem is that this division method does not actually divide the value of the ground collision, meaning that it doesn't sum up to the value of the ground collision. There is something left, and that's something what we don't want. And that's the axiom of efficiency. So the axiom of efficiency says that you want the value of the ground collision to be exactly divided among the players. You don't want to have any leftovers, or you don't want to give them more than you have. And there is this famous Shapley value that satisfies these 4 axioms. In the previous presentations, you've seen the translation of this axiom to the context of explainability. There are various ways you can try to translate it. That's out of the scope of our talk, but well, I'm happy to discuss it with you in private. Okay, so Shapley value, the famous result, it's uniquely determined by these 4 axioms. And if you look at the space of all possible solutions, Shapley value is this one interesting solution in this space. And let me give you the intuition given by Shapley. So there's this, let's say, pictorial representation of it. You have players entering a room in different queues. So we have 6 permutations. And then if you want to get the Shapley value of player A1, you assume that all the players before A1 in the permutation are already in the room. And then you compute the marginal contribution for each queue, for each permutation. So we do that. We compute these marginal contributions, and then we compute the average. And of course, in our symmetric game, the result will be symmetric. That's fairness of the Shapley value. So the Shapley value solves our previous 2 problems. It's unique. It's uniquely determined by these 4 axioms. And it also distributes the value of the ground collision. So that's the axiomatization of Shapley. However, there are many other axiomatizations. It's actually a sport in game theory to axiomatize the Shapley value. And top people do that. If you want to be top game theorists, you try to axiomatize the Shapley value. So Meyerson, Nobel Prize winner. Young, almost Nobel Prize winner. Hart and Mascolo. Mascolo is the author of the most difficult PhD book for PhD students in economics, like a Bible for economics, I mean, PhD students in economics. And then Oskar Skipski, my PhD student, thank you. He, as you can see, he did, you can see that efficiency axiom appears everywhere here. And in his axiomatization, there is no efficiency axiom. And actually his axiomatization is very interesting. He axiomatized the Shapley value using a bit stronger version of additivity axiom and some border conditions. So it's actually a unique axiom, I mean, single axiom plus some border condition. Okay, so let's compare these 2 methods that we discussed so far. We have the Shapley value, which is the weighted average marginal contribution to all collisions. You see, this is this this weight before the marginal contribution. It satisfies all these three axioms, and it's uniquely determined by that. And then before we discuss this simple average marginal contribution to all collisions. And this satisfied these three axioms, but was not uniquely determined by these three axioms. And this thing is exactly the Banzhaf value, right? So this method of dividing the payoff, it's called the Banzhaf value, and it's also a dot in our space. It's basic. It also has axiomatic systems that support it, that uniquely determine the Banzhaf value. That's one of it, introduced by Heller in 1994. And of course, you can ask the question, what about the efficiency? So why you want efficiency? Because in the SHAP method, efficiency allows you to add up all the values of the features that you explain. They add up to the total value of that is returned by the model. And you would like to have it, right? It's kind of like sanity check. Can you have efficiency with the Banzhaf value? Well, it comes out that you can. What you have to do, you have to just normalize it. So the way to do that is just give to every agent, give to every feature the proportion of the grand collision that is produced by the corresponding Banzhaf value. And then, of course, the question is, what about the axioms? And it comes out that this normalized Banzhaf value is also axiomatized by Van den Brink and Van der Laan, and there are also some other axiomatizations. And there is this, of course, efficiency axiom, because this clearly satisfies efficiency. And there are some strange other axioms that you see, and you may say, well, these axioms look strange. But then the same authors showed that actually the Shapley value satisfies the same axioms. And the only axiom that differs is the very last one. You don't need proportional proxy agreement, but what you need is coalitional unanimity proxy agreement. It's a very mild difference. So what I'm just showing you is that it's not outrageous value. It's not an outrageous way of measuring impact of a feature. Okay, so there are also other conceptual issues when you think of using the Shapley value to explain your model. So first of all, why do we really look at permutations? Because Shapley value does look at permutations. Why do you have to look at, why does it matter for explaining the model, the features that are already in the model, already considered, and those that are not yet considered, and the ordering of them? Then why the vector of features man 40 years should be different from the vector 40 years man. And then, well, there is this discussion in the weighted voting games literature, because they use a lot Banzhaf value and the Shapley value. And there is actually, well, what they found is that even if you have a very nice axioms, when you talk about values, very basic axioms that you believe it's intuitive, obviously it should be like that, it may lead to paradoxes. Actually, some authors suggested that whenever you have a choice between Shapley and Banzhaf, what you should do, you should go with kind of intuitive approach, that whenever you believe that order of variables matters, use Shapley value, because there is an order of variables. Whenever you believe that it doesn't matter, use the Banzhaf value, because it's just more, if it doesn't matter, it doesn't matter. All right, so look at the probabilistic interpretation of the Shapley value. Look at actually here. That's one of the this is one of the unintuitive things about the Shapley value, that the Shapley value assumes that the probability that an agent is going to contribute to a collision of a certain size is the same for every size of the collision. So here, the probability that agent A1 is going to contribute to the coalitions of size 0 is exactly the same as it's going to contribute to coalition of size 1 or coalition of size 2, right? And this is not intuitive in certain settings because, well, think of, you can use the Shapley value of the probability that your company is going to go bankrupt, like, or things like that. I mean, there are like many applications of the sort in economics. For instance, you can think of banks going bankrupt. So what's the probability that, I mean, you cannot, I mean, this model assumes that the probability that one bank is going to go bankrupt or the group of 2 banks is going to go bankrupt is the same as the probability that 50 banks are going to go bankrupt. That's not rational in certain settings. Maybe in some other settings it is. Anyway, there are other versions of the extensions of the Shapley value that basically assume that you can change this probability of an agent entering a coalition of a certain size. You can modify it to whatever you want. And with this way, you obtain so-called semi-values. And the Banzhaf value and the Shapley value are 2 prominent semi-values. And there are, so whenever you need to, in your application, I mean, like big coalitions are improbable. You can modify this in your definition of the value. There is no problem. And in certain, I mean, there are, to change it, it's actually increases by the order of magnitude your computational time, but it's not such a big problem. Well, so talking about computational challenge, both the Banzhaf value and the Shapley value are difficult. It's 2 to the n. So how you deal with it in game theory? You cannot cope with it other than changing the model of the game, right? Because you need to decrease the number of degrees of freedom of the model. You need to have less variables in the model. And one prominent example of it is Denk and Papadimitriou, 1994. He proposed, this Papadimitriou, yes, he proposed to describe the game on a graph where agents are nodes, and then the value of the coalition is the value of the edges of the induced subgraph by the coalition, right? So the value of this coalition A1, A2 is the self edge, the value of the self edge of the first agent, the second agent, plus the edge between them. And the beauty of this representation, first, it's concise, so you don't need 2 to the n values. Of course, you cannot express many games, but there are many games that you can express with this representation. And also, the beautiful thing is that you can compute the Shapley value in linear time, because the Shapley value of agent A1 is basically the self edge plus half of the adjacent edges, which comes from symmetry of the Shapley value, of course. And there are many results in game theory, in computational game theory, that show that you can actually compute Shapley value or many other values in polynomial time for many such representations, especially when you have graphs involved, right? So coming back to the presentation that you've seen, that you've just seen, it's quite probable that for the graphs that we've seen, you can compute the Shapley value faster than using a typical method. So let us show us our algorithm very quickly because I'm running out of time. So the 3-SHAP algorithm computes the Shapley value in a TLD squared time. T is the number of trees, L is the number of leaves, D is the depth, the maximum depth of the tree. And they don't have the algorithm for the Banzhaf value, of course. What we do, we propose an algorithm that computes the Banzhaf value in the time TL. And the method that we use can be extended to improve the Lundberg and colleagues algorithm to TLD time. Well, that's a graphical representation how this algorithm works. I'm going to skip it for now. It's basically a dynamic algorithm. I mean, that's a Lundberg and colleagues. That's how our algorithm works. And trust me, it's nice. And if I had 5 minutes more, I would probably tell you more about it, okay? I'm happy to talk. I mean, I don't know what food is going to be here, but I'm happy to talk about it at that time. So let's talk about the advantages of the Banzhaf value. So what we do, we use two popular implementations, sklearn and XGBoost. These are the data sets we used, well, also known ones if you study that stuff. These are the hyperparameters and the results. So the running times, we are better, right? For both implementations. Also, we compared qualitative difference, and to wrap it up, there is no qualitative difference between the results. If you look at what happens for the smaller data sets, you have no difference at all between the Shapley value and the Banzhaf value. For the bigger data set, the one with 1.5 million rows and 650 variables or something, this flight, you had differences on the 9th and 10th most important, in the queue of the most important variables is very little. We also studied the Cayley distance, so the distance between two vectors. I mean, when you have permutations, two permutations, you can, it's a number of swaps you need to get from one permutation to another. I have a very nice slides for it, so I'm going to show you them, right? I mean, you've seen it. And then, well, also, these are these Cayley differences for for permutations of size 3, 10, and 20, right? And you can see that for 3, it's like, for the small data sets, it's very, very small. The differences are very, very small. And when you have larger tree depths in these models, then the differences are a bit bigger, but they are still very small, right? We also compared average errors, and they are also very small. So basically, qualitatively, there is no difference between Shapley and Banzhaf, and you can compute it faster. And it's noticeable when you do it in real life and you train your models. And finally, the final advantage of the Banzhaf value is numerical accuracy. And actually, from this study of errors, we noticed that there must be some numerical problems with the Shapley value, especially for bigger trees with larger depth. And indeed, when we studied that, what we can show is that Banzhaf is numerically stable, to the certain point, to the certain depth of the tree, Banzhaf value is numerically stable, while the Shapley value, this blue line is for the Shapley value, becomes, in our simulations, numerically unstable. But we cannot prove it formally at all. So what we can only say is that our results suggest that Banzhaf is much more numerically stable. So I hope I convinced you that there are very many nice other solution concepts in game theory than the Shapley value. It's very interesting to look at them. And I hope I convinced you that for 3 models, it's worth at least to look at the Banzhaf value, not only the Shapley value, because it's faster to compute it. We are planning to release a library that is going to be freely available with the Banzhaf value. So I hope you are going to use it. Yeah, and if you have any questions, then you have emails of my co-authors. Thank you.
Great. Thank you, Tom, for fantastic talk. Do we have any questions? Okay, there's one question already.
Hi, thanks. So I have 2 questions, and maybe you can answer the one that you think is more interesting. So one, if I understood correctly, is that you focus on like binary feature, if something exists or doesn't exist.
Yes.
But is there some extensions to non-binary features? That's the first question. And then the second question is, so you get this fairness value. So if you didn't include, if this Boolean was not true, how would this value, output value change, right?
Yeah.
So how do you get the ground truth for evaluation of that? Because so you get the value, how much the target value would change if this feature was not present in your feature set.
Oh,
And then how do you get the ground truth? What actually is this actually correct prediction? So
well,
there's two questions.
I
Maybe one
get
of
it.
them.
So let's don't talk about the second question, because it's I mean I'm perfectly. I mean, I haven't played with that myself, so I wouldn't like to say something that is not true.
Sure.
And the first question was,
yeah, so like we are assuming here that we have Boolean features, so something is either present or not, and then it's not always the case. Sometimes you have like real values. So for example, for the Boston housing data set, it's some of the values are real values, not Boolean values. So
well, again, it should be. I mean, I haven't done the experiments myself, so that's something that I will have to ask my co-authors. I was more into the game theoretic part for that. So sorry, I cannot answer that.
Okay, thanks.
Yeah.
All right. Do we have some other questions? So this was the last talk, so we have time now until you are hungry, basically. Okay.
Thanks. So maybe first, before a question, maybe an answer to this Boolean value. So it's here the Boolean value means if we include a feature or not the feature exactly must be Boolean. So I think that's So the correlation means that we include some number of features and not, or we have a smaller correlation. So that's so. And the question is, like this normalization is pretty intuitive for Banzhaf value, and so why it wasn't like used earlier? Like why the focus on Shapley value? Do you know why?
Well, yeah, because well, I haven't yet finished this presentation. You could see that this egg figure. I mean, this. Oh, sorry, I turned it off actually. So there is this egg figure there. It's 155 slides exactly. So I think at slide 100 we are going to be in the place where I want to be. So there is this figure somewhere. So basically, okay. So let's don't go back. So basically, there is this. The Shapley value is on the interface of many types of values. So you can have another X shapes in this big X shape with all the possible solution concepts. And indeed, the Shapley value is like the center of many different solution concepts, but it doesn't mean that it's the most intuitive concept everywhere. As I told you, okay, so let me reiterate this example. The European Central Bank says that certain banks in the financial system are more important than others. And they actually they tax certain banks. They tell them to pay more money to this special fund for the time of the crisis. And they say, if the bank is responsible for more transfers between the banks, then it's systemically important to the financial system. And now they actually suggested to use the betweenness centrality to compute how banks are important. And it's good to use, the betweenness centrality is basically the centrality in the graph that computes the number of shortest paths that the particular node controls, lays on. And now they say, if a bank is on a shortest paths in the financial network, on many shortest paths, it's an important bank, and we should tax it. Right? Because if it collapses, then we have to bail it out. We have to give it money to keep it afloat. And now you can show that it's much better. And there were proposals to use the Shapley value for that, because the Shapley value is going to, because the European Central Banks assumes that banks are going to bankrupt one by one, because you compute the betweenness centrality you make a ranking of banks according to individual betweenness. But actually what you should do, you should assume that banks bankrupt in groups. And you can compute something what is called Shapley value betweenness centrality. So we compute the average marginal contribution of a bank, how many new shortest paths it brings to the group of banks that may collapse, right? And that's the Shapley value. And that's not good. I mean, that's not a bad idea, but the problem is that this assumes that the probability that one bank or 3 banks collapse is the same that 10 banks collapse. And it's not good, right? I mean, it's much better to use some other semi-value, like a Banzhaf value or any other semi-value that has a different distribution of probability of collision sizes that an agent enters to, right? So, so the Shapley value is the most known, is the first value, but it doesn't mean that it's the best one, you know, for every application. And once you know it, you open your mind that, well, maybe you can do something better, something different. And typically, when you compute semi-values, it only increases the computational time quadratically. However, well, it's actually my specialty to compute the Shapley value in polynomial time. And there are many, many nice examples that you can compute the Shapley value in polynomial time. I mean, whenever you have a concise structure like a graph, I can tell you that in many cases it's doable.
Thanks.
Right.
Right, thank you.
Sorry, I'm in love in Shapley
Okay.
value and related concepts. So you can probably see that.
Do we have more questions? If not, then I think
We are hungry.
it's time
Thank you.
for after party. So let's thank Tomek once again for a great presentation. Thank you.